So good evening to this demo lecture on computer organization and architecture. It will be a very small lecture to basically tell you about the course, and basically I'll just tell you one small concept that will help you understand why is this course important and what is the nature of this course. Okay. And the thing is that you will only be answering the questions because you know many of the things that I will teach. I just want to extract it from you. Okay. How many of you here have written ever a C program? Any C program, maybe even Hello World is fine. Every one of you have written here? Okay, good. So basically, why did I ask you this question and what's the importance? The importance is that in this question, in this lecture, we will look at starting from a C program, how does a computer execute the first instruction? So basically, the thing is this. First, what I will do is I will ask you that what are the steps that are taken when you are writing a C program. For example, what are the steps? First step is you write a C program, write a file, and let's call it program1.c. Where do you save it? You save it in the hard disk, right? Your C drive, D drive, E drive. You save your program in the hard disk. So if I draw it diagrammatically things look like this. So your first program, which you are trying to execute, you wrote a C program, and the C program is present in something called the hard disk. And the hard disk is a memory storage where you can store your data in. It's a slow storage, slow in the sense the speed of access is very slow, but it provides you a lot of storage. For example, you have probably seen a 1 TB hard disk, right? But it's not easy to see, or it's not possible to see a 1 TB RAM as of today, right? 1 TB hard disk is easier to see because the thing is there's always a speed and size trade-off. More the speed, less will be the size. Lesser the speed, more will be the size. So again, what do you do? What did we do first? The first thing we do was we write a file, we call it program1.c, we save it in the hard disk. Okay. Now, can I execute this program as it is on the computer, or do I need to do something before executing it? There is something called a compiler. What does the compiler do? What will it do? Or what is the command? How should I use the compiler? I have written a prog1.c. What should I do next step? Maybe I can write something like this. So I can compile the program. And what do you mean by compiling? It means that your program1.c, what you have written, is in English, plain English, which the computer does not understand. Computer only understands binary. It only understands zeros and ones. So we need a way to convert our program from text to binary. That's when we compile the program. There is a very popular compiler existing on today, which is called GCC. Has anyone of you heard of GCC? Very good, Roshni. Okay, so GCC is a very popular compiler that you can use to compile your program. And what I do is I run this command called GCC with the program1.c, and I specify the output. It should be in prog1. Even if you don't specify this, then on Linux the output file is a.out, right? There's a file emitted called a.out. Now I have a question here, and think and answer. This a.out, where it is present? When you compile your program, you receive a file, right? You receive something called a.out. You receive the object file. Where is this object file present? You have two options. One option is either in the secondary memory, which is the hard disk, or it is stored in the CPU. CPU is basically the one that contains your chip. It could be an Intel chip or an AMD chip or whatever. Where is your file present? Okay. Now see, why do you say file1.c is in the hard disk? Because it is living in a location, maybe something like this, something like d/my programs /file.c, right? That's why it's in the hard disk, because the hard disk is mounted at this D drive, maybe D, C, E, F could be anything, but I'm just taking an example as D drive. And when you compile the program, isn't the file present at the same place? Yes or no? Have you guys compiled a program ever? You'll see that this a.out is in the same place as file.c, right? It's not in any other place. Correct? So which part of the, where is the a.out present? It is present in the secondary memory again. It is present in the secondary memory only. Okay. Now the story so far. We wrote a C program. We want to execute the C program. So we can't really run the C program as it is. What we do is we use a compiler which compiles this C program from a language that we understand to a language that the machine understands. Okay. And the entire mechanism of compiling, entire mechanism of compilation from file.c to a.out, this entire mechanism is governed by your compiler design subject. There is a subject in your gate which will come up later. It's called compiler design, CD. Compiler design will be responsible for ensuring, will teach you how you can convert this program from file.c to a.out. Now, since we are talking about COA, we are not in the compiler space. So I will take it as a black box, basically telling you that, boss, you have written a file.c, okay? You pass it through GCC and you get a a.out. This is what the compiler will do. Okay, think of this for now. Later on, what are the internal details of a compiler? How does a compiler work? How does this program gets translated? All will be covered in the compiler design course. So we are still in the, still not entered the COA territory. So we got an a.out. Okay. Now, people who have executed a program, especially on Linux, what do you do next? You got an a.out. What do you now do now? Does the program start executing? Or there is a command you write? Don't you write ./a.out after compilation? After you compile this program, don't you write this command always ./a.out? Right? What are you doing here? You are basically running the program. Okay. And what happens when you run the program? What happens behind the scenes? First of all, I told very clearly in some time back that this secondary memory, right? There is a problem with the secondary memory essence that it is very slow. Okay. The instructions that you have written in the program, the CPU will execute those instructions. CPU is here, your hard disk is here. Okay. The problem is, if CPU starts reading the program from the hard disk and executing that program, that will be something very slow. It will be very slow for the CPU. You won't get the speed that you are expecting. So how did the computer designers fix this problem? How did this speed issue was resolved? I'll give you one hint. Have you ever heard of a term called RAM? My phone has 4 GB RAM. My phone has 8 GB RAM. My laptop has 16 GB RAM. Have you heard of this term called RAM? Yes? Okay. What is the full form of RAM? Anyone who knows? I know I have not taught RAM, but since it's a very common terminology, I think random access memory. Perfect. So this is the hard disk. This is the CPU. There is another high speed memory which sits in the middle. It is called the RAM. RAM or random access memory. Random access memory, and normally your RAM will be of very less size. Maybe RAM is something like 8 GB RAM, or nowadays 8 GB is very common, maybe 16 GB RAM, right? And your hard disk here is much of higher space, maybe 1 TB hard disk, maybe 512 GB hard disk, right? So RAM is 16 GB, let's say. Okay. Now the compromise that you get is you are having lesser size, but it is faster than the hard disk. Why it is faster? That is one topic in COA that we will cover later on. But assume now that RAM is just listen that RAM is a space with a smaller size, but it is much more faster. Okay. Now our program is still in A.out. I told you that if somehow I can bring this A.out to the RAM, suppose I can bring it to the RAM, then what will happen is my program will start, my CPU will, instead of talking to the hard disk, my CPU will now talk to the RAM, which will be faster. Is this point clear? Again, let me tell you what is happening. This A.out that you compiled, it is still in the hard disk. It is not in the RAM. It is still not in the RAM, right? It is in the hard disk. If the CPU talks to the hard disk and gets the instructions one by one and executes, it will eventually finish execution. But the problem is it will be very slow, because reading the hard disk is a very slow process. It's a very slow job. It's a mechanical device. I don't want to give much details now because you will be confused, but it is very slow. So what we found out that, boss, we can have a high speed memory in between the CPU and the hard disk. But now the problem is that my A.out is still in the hard disk. It is not in the RAM. So how do I bring it to the RAM? This process is called program loading. This is a topic very famous in your operating systems course, because this program loading is done by the operating system, whether it is you are running on Linux, or you are running on Windows, or you are running on Mac, whatever. The process of loading the program from the hard disk to the RAM is the job of the operating system, and this is very extensively covered in the operating systems course. Okay. Okay, any questions so far? You can ask anything. I'm not really teaching you CO. I'm teaching you basic how does a program starts execution. So could be anything. No questions? Okay. Now we have our A.out here. We have bought our A.out from the hard disk. We have loaded the program to the RAM. Now who does it? When does this loading happen? It happens when you write this A.out. When you write this ./A.out in the terminal, that's when you're saying you're executing it. Basically, first step that happens is you load the program from the hard disk to the RAM. Okay. Now what happens is, now the CPU will start executing code from the RAM. Okay. Now the CPU will, your A.out is there. Your CPU will start reading the instructions from A.out and execute the program. This territory is the COA territory. How does your CPU take an instruction from the RAM and starts executing it? This part, this interaction is your COA subject. There are many things involved here. Okay. First thing is, let me ask you one question. Okay. You first acknowledge whether it is a, did you understand the problem or not? Okay. The solution we will look at later. The thing is this, okay. There are, so, okay. Any program that the operating system, that the CPU is executing, is present in the RAM. Any program. Do you run only one program in your computer? Do you understand the question? The question is, do you run only one program always? Or there are multiple programs running always? For example, you might be listening to music and solving a problem. You might be watching YouTube and reading your notes. You might be running a web browser and your clock is running always. So all these are programs that get executed. One of the program that is executed is maybe the clock process. Okay. The clock process is basically responsible for updating the system clock. The clock, the time that you see. And let's say there is one more program which you are maybe we are running this IGC website on. Maybe it's a Google Chrome browser or a Firefox browser, whatever it is. So that is one program that you are currently executing, right? So there are multiple processes that are being executed. Now what happens is, when the operating system has loaded this a dot out, let's say this a dot out is loaded here. Okay, let's say this a dot out is loaded here. Okay, now the thing is, how does the CPU know that I have to execute the instructions that are starting from this location here in a dot out? How will the CPU know that? Okay, the thing is, the CPU has some storage as well. The CPU also maintains some storage area as well. They are called registers. Okay, register is basically a storage area. And what will happen is, whatever this address this a dot out is in, let's say this is in A1, the CPU will store that address in a particular register. The name of it is called program counter, but I will go to that in detail when we look at the course. And this register program counter is loaded with the address A1 by the operating system. Now, once the operating system has loaded the program and fed the address A1 to the program counter register, that's when the CPU starts executing the program starting from the address A1. Now, how does the CPU start executing the program? That is what we will be studying as part of our COA subject. Now, there is one more thing. Okay, this is one part of the COA course. Okay, basically from the CPU, how does the instructions get executed from the RAM? Now, it so happens, okay, sometimes it happens that when you write a C program, right, you may execute one instruction more than once, maybe 100 times. Okay, can you think and answer what is the C program where you can execute one instruction more than once? How can you execute an instruction more than once in a C program? The same instruction. What is the name of that? Using a loop. Very good, Rashmi. So if I write a loop, let's say I write for int I equal to 0, I less than 1, maybe 10,000, I plus plus, right? And there is some code I am executing here, let's say S1. Now the problem is, people wanted to optimize further. In the sense, what they wanted to do was, this instruction S1 is present in this a dot out. It is present here in the RAM. Okay. Now, what scientists decided, okay, this again, scientists were deciding that, boss, I think this S1, right, is executed again and again. Is executed again and again, it is executed. So, do one thing. I will have even a faster memory in between my RAM and CPU. And what I will do is, I will only store S1 here. Okay. What now will happen is when the CPU has executed the instruction first time S1, it takes it from the memory, but subsequent times when it tries to access this instruction, it is accessed from this high speed memory. See what's happening. Okay, first we had the hard disk. Turns out that the hard disk was very slow, so we introduced the RAM. RAM is a smaller space than hard disk but much faster. It turns out that even there are some part of the code which is run so frequently, like in this scenario, that scientists decided that we will have even a faster memory but even of smaller size in between the CPU and the RAM. The name of this memory is called cache. Okay, the name of this memory is called cache. Very good, Rashni. So cache is a high-speed memory that sits between the CPU and the RAM, and it is responsible for executing faster accesses. Okay. Now, I know I have really fed you a lot of things, so let me now try to consolidate things and bring it up as a story. Where did we start from? We started from the fact that we wrote a C program. Okay. Now, first question, where is the C program present? Please answer. Where is the C program present? Which memory? It is present in the dash hard disk, secondary memory. Very good. When I come, so can I run this C program directly? Answer is no. I cannot run it because this C program is written in textual format, but the CPU only understands binary. So is there something I can do that I can convert a C program to a binary representation? I use something called a compiler. Okay. Now this compiled program, after I use the compiler, the a.out that is generated, where is this a.out present? Where is this a.out present? Anyone? Again the hard disk. Now, as I told you, the CPU, if it starts executing the program from the hard disk, it will take a lot of time, right? It is slow. So what we thought was, let's introduce a high speed memory in between the CPU and the hard disk. What is this high speed memory called? It's called the RAM. And who is responsible for loading the program from the hard disk to the RAM? The operating system. Very good. Now, once the program is there in the RAM, the CPU can get to know from this. Okay, so already the RAM is executing some other programs like this web browser which you are using to watch this video, or the process that uses the clock. Already you are using it. Already these programs are executing. How will the CPU know that, boss, now you have to start executing the address, the program a.out that I just loaded? Because what we do is when we write this a.out /a.out, our intention is to run the program. We don't want the CPU to say that, hey boss, I'm already running something, sorry I can't do it. No, I want this to run because that's what I'm doing. So the operating system, when it loads the program in the RAM, it will load it at a particular address. Address is basically a location inside our RAM where this program will be loaded. So it will load at some address. I call this address A1. Now this address A1, how will the CPU know that the operating system has loaded this program at address A1? The CPU maintains some storage area called registers. And there is one register called the program counter, whose job is to tell the CPU which is the next address that you need to execute. And A1 will be stored in the CPU, in the program counter register of the CPU. And once the program counter is updated, CPU can now proceed. CPU will basically go to the RAM, check at address A1, read this instruction, put it in the cache, starts executing. Next instruction, put it in the cache, start executing. Like this, it keeps on executing the instructions. Now, what is the use of a cache? What scientists again figured out was, boss, there are some instructions which are executed again and again, more than once, right? So what I can do is faster access to frequent instruction. Perfect answer, Roshni. Couldn't have been any better. So what Roshni is saying is, if you are executing a frequent instruction meaning an instruction execution more than once, like in this scenario. Now, in this case, what I will do is this S1, this instruction S1, instead of keeping on reading it from the main memory, I will have a faster memory in between these two called the cache. Now, why it is faster? What is the reason behind them? Behind these three, they are the technology by which they are made. For example, hard disk is made as a electromechanical device. It's a mechanical components that run. That's why it's slow. RAM is called a DRAM. I know it will not make sense now, but just these are all which is coming up later on. And cache is basically something called an SRAM or static RAM. So that's the reason of the technology that is different between these three memory storage modules that make it faster and slower. So again, coming back, this S1 is an instruction which is executed more than once in the RAM, so it is brought to the cache, and now the CPU will talk to the cache more often than the RAM. So that is the entire story, and this region that I am talking about, this region is your COA subject. Okay, this is your COA subject. Basically, how does the CPU execute the program? What is the role of the cache? How is a cache designed? How is a RAM designed? How is even a hard disk designed? And how much time does it take? What are the different optimization that the CPU applies in order to run programs faster? All these technologies are covered in the topic COA. Okay, so I hope you got to learn something and I did not confuse you. Is there any questions with anything that I said so far? Any questions? Anyone? No? Okay. Okay. So let's go to the basically the syllabus. So what are we covering? What are the topics in this course? So we'll start from memory hierarchy, which is the cache, main memory, and the secondary storage. Okay. This is very important topic. Then we will move on to what is a machine instruction, and we'll look at something called addressing modes. Then we will look at the ALU data path and control unit, another very important component for your CPU. Then we will look at how CPU optimizes executing more than one instruction by using something called pipelining. And then finally, we have something called an IO interface, which talks about how the interrupt and DMA mode works. Okay, so this is your entire syllabus. Okay, any questions? I think I have finished what I had to cover, but if there are any questions, let me know. Anything you want me to, anything you want to know from the COA subject point of view? How important it is? What is the weightage? What is how is will it help me for any other course? Any questions that you have? Maybe on the technical side as well. See, honestly saying, Ronak, this is a bit complex. Okay, I won't sugarcoat saying it's a scoring subject like maybe discrete or TOC coming up. It's a bit complex, but the thing is, um, I took a lot of time to learn this subject. Okay, honestly saying, and it. I also have done an advanced architecture course in my IIT coursework. So it is difficult, but if you just with my with whatever I say, watch the lectures and then um, understand the stuff, and you will be okay. Okay, but yeah, it is a bit complex, but the good thing is, if you have a good hold on this subject, then you are set for compilers and other subjects as well. So it's an important subject, but a bit complex. And but the good thing is, the good thing about this subject is, even though the concepts are complex, the questions that come in the gate are simple. Okay, any other questions? Okay, one thing is the book, right? So again, you may listen to my lectures and solve the PYQs, which is enough. But there is one good book. I will give you the exact name. Um, it's called Computer Organization by Carl Hamacher. Okay, you can also get a PDF of it. You do not have to buy it, but it's a good book and it can help you to clear your concepts. And one more thing is, so the industry where I work at today, they I work very closely with the subjects with the topics that I will cover as part of this course. Okay, so I also have a bit of an industrial perspective on how these things work in the industry, especially from the perspective of semiconductor companies. So I can also give you the practical insights on basically what these different things, how they work under the hood. Okay, and if you want to venture into that space of working in semiconductor companies or working in the space of systems programming, anyway, I believe SDE jobs are anyway will be, I won't say extinct, but it will be very difficult to get after some years. So more systems related people, more people who can understand how to optimize AI kernels from the perspective of architecture and compiler will be a much bigger skill compared to using AI to do stuff, which maybe many companies today do. So if you want to venture out in that field, in this field where I am in, this subject is super important for you. Okay, if you want to cover a master's course in IIT Madras or anywhere in any IIT on systems domain, especially on the architecture side of things or the compiler, only one thing you have to do is you have to make sure you are very serious in this subject. Okay, because this subject is basically something that you must know if you are looking for those kind of jobs. Okay, so please remember that aspect, and my suggestion is, now I believe there is questions, there is systems related roles a lot more important, and lot more importance of that roles are present because there are many companies, there are shortage of people in these semiconductor companies which are looking for people of this expertise. So it's a good venture to be in if you're looking for jobs. Okay, what else, any other questions anyone has? Good question. Yeah, I was waiting for this question. So the weightage of this chapter of this subject, okay, is about 10%. Okay, every year they ask a lot of questions, and the reason why I'm telling you a lot of questions is there is a big overlap between this subject and operating system. Sukatirtha. Okay. Basically, if I give you another detail, in operating system, you learn a concept called paging and TLB. Okay, if you haven't learned it, just listen. Okay, you will learn a concept called paging and TLB, which is basically how is the program loaded from the HDD to the RAM. The problem is this. The problem. Let me explain you the problem that operating system is solving. Your RAM is only 4 GB. If I ask you a question, let's say I want to run a program of size 100 GB or 10 GB, let's say. My RAM is only 4 GB. Okay, but my program is 10 GB. So it turns out I won't be able to execute. But the thing is, operating system is able to solve it by doing something called paging. So that is one part of the operating system. And once the program is loaded here, then the cache comes into the picture. That is a COA part. So what I'm trying to say is there is a lot of overlap between operating system and COA. Okay, so if I include that as well, then easily it is 20 to 25% on average that the weightage is of COA in the gate. Okay, and one more thing is the memory hierarchy and the pipelining. These two are the most important topics for your gate. Okay, let's say you don't have time to study these subjects or revise this subject. My suggestion will always still be, do not go to the exam without knowing these two concepts. If you don't know these two topics, it's not possible to get a good rank, because lot of questions are asked from memory hierarchy and pipelining, and in the context of computer COA as well as OS. I know I gave a long answer, but does it answer your question, Sukatita? Right. On an average, it is 10 to 15% if I look at only COA, but if I include operating system as well, then it is 20 to 25% easily. Okay. Any other questions? Roshni, Ronak, Mahidar, Sukatirtha. Okay. My small feedback I would need. Did you guys learn anything today from this gyan that I gave? Yes, no. Yes. Okay. Roshni says yes. Others, Ronak, did you understand anything from what I said here? I know there are a lot of things I've just thrown you jargons in the air. I understand that, okay? But the thing is, my job is to make sure you understand each of them. Okay? That you will do eventually when we look at the course. Okay? Okay, then I think if there are no other questions, we can end the call. Uh, we'll talk in the main lecture. Thank you for joining. Please feel free to download the slides. I know there's not much, but still, if you want. Okay, okay, Rana. Thank you. Thanks for joining. Thank you, Sukatirtha. Okay, I think we can end.